All right, there we go.
All right, so the first lab we're doing on Friday, I would like you to print it out. It should be under the lab part of the course, the 110A. And I think there's only one lab showing. It's the graphing lab. So please have that printed out when you come to the lab. Oh, also, before that lab, please make sure you watch the lab orientation videos. For those who've had me before, they haven't changed. So if you remember what they were before, I guess you're ahead of the game. So if I take two objects that are same size but different weights. This one weighs roughly 4 times more than this one does. This is brass, this is aluminum. Not a trick there. If you wish, if you're not convinced, I can hand it to you. You can see that this one weighs more. Would anyone care to just verify? Nothing up my sleeves. I guess you'll trust me. If I drop them at the same time, which one will hit first? And there are a number of people, I mean, there's a variety of answers that I just saw just then. And so some people know what's going to happen, and some people do not know what's going to happen. So let's just see what happens. 3, 2, 1. So for some of you, I think you'll realize that for the first answer, you got it wrong. But that's part of the learning process. It definitely blew your minds just then. In a good way, not as in you'll never recover from the damage. I hope. So what we're going to do first is I need 3 volunteers. 3 volunteers. Thank you. 1, 2, 3. All right. Between the 3 of you, decide which one of you is the weakest. And so that is Chase, and then 2 names I did not write down here. Genesis, that's right. And Ashlyn. Oh, I did have that written down, just in the wrong place. Okay. All right, so Genesis, Ashlyn, and Chase decide which one of you is the weakest. But everybody, let's head out into the hallway. And I have enough footage of blank boards that we will. Thank you. Now, one possibility is that Genesis is just incredibly strong. He's lying about her weakness, and they're just waiting for sand to be kicked in their face. Those who don't get that reference, ask your parents. Are you just so incredibly strong? There we go. Answers that. But just for the sake of argument, let's assume that she were the weakest. How could she do that? Why did they not have a chance? In spite of, or just not regarding just how incredibly strong she is.
Because she was in the middle.
Because
she was in the middle.
And what does being in the middle do? Pardon?
She was like a 5-4 stalwarts.
And why does that mean that she was able to overpower them?
Because she's throwing off the balance in the middle.
Louder, please.
Because she's throwing off like balance in the middle.
What do you mean by that?
Because she's in the middle and they're not like, I guess they weren't pulling at like the same force.
It actually is going to turn out that they were pretty much applying the same force. That the tension in the rope was pretty much the same throughout.
Because gravity was over.
That should be a very small effect. The weight of this, the gravitational force acting on it, or its weight, it's small enough that I can lift it easily with my bad arms. So that's not the main cause here of that. Robert?
Because their forces negated each other.
Why?
Because they were pulling in opposite directions.
More specifically, why were they not keeping her from putting it on the ground?
Because her force was greater than their two canceled forces. I'm trying to word it right.
So close.
I know.
Or force is going opposite directions, hers is going down.
That connects it with the down. Most of the effort that Chase and Ashton were spending were against whom?
Each other.
Yeah. Very little, especially at the beginning, very little of what Genesis was doing was getting opposed. Because starting out, all the force that they were exerting was that way, and she's going this way. They're not opposing that. Now, as the rope bends, now they're pulling, now Ashlyn and Chase are pulling up and out. Still, most of their effort is outwards, and some of their effort is upwards. But it is pretty much, it's very difficult to keep the person touching the ground, touching the rope to the ground, unless there's just such an incredible height difference that the person in the middle can't touch it. So, what is the lesson from this? There are certain quantities that we will deal with where direction matters. There's certain quantities that we'll deal with where direction doesn't matter. Number of people in the classroom. There's no direction involved in that. It's just a straight up number. However, there are some quantities, some things that we will measure where direction matters and some things where it does not. Now, if something where the direction matters, so if I have something with a direction and a magnitude, so in this case right here, we'll just take Chase. Chase was applying a certain amount of force. We could quantify that in a direction, so we needed both things there. We will be dealing with things, these things that involve both of these are called vectors. And vector math is a little bit different than scalar math. Spoiler for the next one. If direction does not matter, so we have a magnitude but no direction, magnitude, amount, size. Scalar math you've been doing. I suspect not many of your elementary school teachers called it scalar math. Just, by the way, did any of them? When I taught elementary school for a year, and I made sure I used that term just because when they get here, when they finally take physics, they go, we've been dealing with scalars all our lives. Now, how do you know if something's a vector or a scalar? Well, there are certain clues to it. First, the visual clues. If I have a vector, which I'm going to, first off, physicists, mathematicians don't like writing. We want to write as efficiently as possible. So what we're going to do is come up with these symbols to represent things. Just because I don't feel like, I'm not going to write the word east or west out. I'm going to come up with a quick little symbol and an arrow and be done with it. So I'm not going to write the word vector out, typically. If I have something that is I'm going to represent as a vector, I'm going to put a little vector symbol over it. And this just means we worry about magnitude and direction. Now, who in here has dealt with vectors before? This is there are a couple of different ways of writing this vector symbol. That's one of them. That's the way I typically do it in class, or if I'm in a hurry, it'll look kind of like that, but a lot sloppier. On a test or quiz, they're doing the printing, it'll probably look like that. It can also look like a double print. I do that for one thing, we'll get to it at some point. And then in textbooks, this is not easy to do on the board, but in textbooks, sometimes textbooks will just do a boldface for the vectors. So those are basically the clues that you're dealing with a vector. All right, I happen to pick F here because F is a force. I often use F for force. Force is a vector quantity, so if ever you're reading a problem and it mentions force, you should immediately think, vector. So an example of a vector is a force. And that's the primary one that we will deal with in chapter 2. In chapter 3, come up with a couple others. Displacement. Actually, I'm going to do another one, write a different one first. Position, then displacement. And yes, I did mention I taught elementary school, and when I taught elementary school, I made sure I wrote much neater than you will see me. At least in my mind, I was a lot neater. It is possible. Velocity. Acceleration. Now, acceleration is a little bit different. These right here, if you see those words right there, they're automatically vectors. Acceleration could be a scalar, could be a vector. Unfortunately, they didn't come up with a new word. An example of words that automatically are scalars. Dramatic pause for questions before I talk about some examples of scalars. All right, an example of a scalar. Mass is a scalar. And sort of nip it in the bud here. Mass and weight are not the same thing. I think they're used interchangeably in biology, maybe chemistry, but in physics they are definitely not the same thing. Mass and weight are not the same. Weight is a force. Mass is mass. Distance is a scalar quantity. So if you see, if I'm asking for distance, I'm asking for a scalar quantity. I'm not worried about direction. Speed is a scalar quantity. And then, as I mentioned before, acceleration is a scalar or a vector. So the question is, how do you know which one you're trying to find? Well, in a textbook, you have to sort of pull it from context. There are times in which you can get two different answers depending upon what the author meant. And on the stuff that I write, I try to put the symbol afterwards. So if I'm talking about acceleration scalar, I have an A after it. If I'm talking about acceleration vector, I'll have the A with the vector symbol over it. Now, as I mentioned before, we don't like writing a whole lot, so I don't want to have to write out force, position, displacement, velocity, acceleration. So I need a shorthand notation for that. As mentioned before, the symbol for force is the capital F. Position. There are 5 basic symbols that are used. I tend to use X out of habit, but X or Y, Z, R, and S tend to be the ones that are used the most. And you can start to see some of the sloppy vector notation I do right there. Displacement is the change in position. Anyone know what the symbol we typically use for change is? exactly. So displacement is, you just put the delta, the triangle, the capital delta, in front of whatever you're using for position. So delta x, delta y, etc. Velocity, the symbol that typically is used is a v with a vector symbol over it. Now Hewitt tends not to use these. Hewitt I think, generally writes the words out. All right, so if ever I'm talking about force, then there's a magnitude and direction in the final answer. Or we're dealing with magnitude and direction. If we are talking about, if I just want one of them, then I will specify what is the magnitude of the force, or what is the direction of the force. Now, if I want just the magnitude of the force, again, this is because I don't feel like writing it out. I'm going to write it out this time and then hopefully not after that. So if I want magnitude of force, that's a whole lot of writing, and again, I don't want them. So the shorthand notation is you basically take your force vector and you want the magnitude, absolute value symbol around it. This is shorthand for magnitude of force. Some textbooks put double lines around it. I tend to just do the single absolute value. Now, as you go on, I'm going to be using the shorthand notations here. If you forget what they mean, just zap. Questions to here before we double the number of symbols? No. It's simpler than I just made it up. We're done at 1:40. Okay. Plenty of time. All right, symbol for mass. Yeah. We use M for a number of things. M also stands for meters, and you have to figure out what M means based on context. All right, so distance is an analog of displacement. So it's whatever you're using for displacement except no vector symbol. So delta x, delta y, and so on. Speed is the scalar analog of velocity. So it's just v without the vector symbol. It is not s. And acceleration reaches just an a. This stuff right here, that's chapter 2. This stuff right here, that's chapter 3. Physicists would love to be able to teach chapter 2 and chapter 3 simultaneously, because they're both setting up the foundation for the rest of the course. Unfortunately, you have to do one then the other. Most textbooks will do this stuff first and then get into this. Hewitt does this, then that, and then comes back to this, which I think might actually be a better way of doing it. However, we'll be dealing with forces, then we'll be dealing with this, and then chapter 4 will connect the two. And on that note, have a lovely day, and I will see you on Thursday, I think. And welcome to the greatest subject you will ever take. Anyone who's had physics before can attest to it. It is the greatest subject ever.
Don't have me lie for you.
What's that?
Don't have me lie for you. I'm back, aren't I?
All right, so what grade do you need? You need a D, right? Is that what we're targeting?
You give me a worse grade than I got in 150.